Hello everyone. On the previous video, we explore the 100 megahertz signal we can find in a PCI Express connector, and we plug it to an SDR, and we managed to see something on the screen, and the shape of the signal was a bit unexpected. We didn't see a clear tone on the screen. In this excellent paper from Texas Instruments, explains help us to understand what we saw and what we can find when it comes to the 100 megahertz signal in PCI clock signal in PCI Express. Link in the description, by the way. So this document explains that the 100 megahertz signal is modulated on purpose, and it's modulated in frequency to have the signal spread across a number of frequencies. Apparently, this on the original design of PCI Express, this was done on purpose to reduce the amount of energy the amount of interferences that this signal could have with thousands and thousands of PCI Express devices using the same precise 100 megahertz tone. So part of the standard is modulating in frequency. I couldn't find a precise definition of the ranges. There are some recommended ranges, and this also could explain why when we were capturing the 100 megahertz signal from different PCI Express devices, we saw different shapes on the screen. I guess different manufacturers changed the intensity or the distribution of the frequency. In any case, this document explains what to expect, and it's very interesting to see how similar the signal we capture when compared to what this document is telling us that the signals should look like. Well, it's obvious. This is a zoom in the capture of one of the captures we did in the previous video, and we can see the similarities, and we can make more sense of it. Before comparing the signal a bit more, in this document, unfortunately, in this spectrum, in this diagram, they're showing us two signals. The document wants to compare a signal modulated, which in this case, in this capture is number one, and a signal that is not modulated, that it's a pure 100 megahertz tone. Unfortunately, both signals are in the same blue color, so even if you download this PDF yourself, it's going to be a bit tricky to see it. But just for illustration purposes, there is this ground noise down here of the signal number 2, that is the signal without modulation, and that shoots straight up to here, and then comes down again. So I think it's here. I think they call it the single 100 megahertz peak at minus 5 dBs, which would be around here, compared to the other one. So that's what the standard intends to do. And I wanted to highlight not only the difference in intensity, which is what the standard is intended to do, but also the position. I find it interesting that the central 100 megahertz, it doesn't sit in the middle of this curve, and this is again, this aligns pretty well with what we found in our previous video, where we could see that this is the 100 megahertz center right here. We had 100 megahertz selected in our spectrum analyzer here, and we could see that the curve was a bit distributed to the left, which again aligns pretty well with what the standard is asking those manufacturers to do. So, well, now we understand why we didn't find a single tone and why we saw this spectrum of frequencies spread across a section of the spectrum. So we got that clarified. So we have detected, we found a 100 megahertz clock signal in the PCI Express. It's a spread spectrum modulated. There is in the receiver end, there is some kind of electronics that is going to remove this modulation, to regenerate and extract that 100 megahertz signal. Perfect. But the second we compare that clock signal with the PCI Express speeds, it's easy to see that it's something not adding up. Even the first version, the PCI Express version, generation 1, is already at 2 to 5 giga transfers per second. And it has been doubling and increasing ever since. And this, at least in my case, for me, I had to scratch my head a bit, because that doesn't align with the classical clock signals used in serial communications. Here we have an example. This is just an example of the SPI serial protocol, and this is a classic diagram where you have the clock signal at the top dictating and helping the rest of the circuits to detect exactly when an information unit begins and ends. And in order to do that, in order to have the clock signal dictating, it has to be as fast, at least as fast as the data itself. In every single period of the clock signal, we're going to have a unit of data. We can have less. We can just decide to ignore the clock signal for a while and have less, but we cannot have more. And that right away, it's got me thinking, how can you have in PCI Express, even in generation 1, 2.5 transfers per second with only a 100 megahertz signal? Something's not adding up. And again, coming back to the same paper, we have it goes a bit, I wouldn't say in detail, but it's a very good introduction of how does this work, how it's possible to transfer through PCI Express, which is it's a serial protocol, higher frequencies with only this base 100 megahertz signal over here. Let's zoom in a bit, and this is the classic. There are many other topologies, and some of them are introduced in this document, but this is the classic where, in this case, the diagram is PCI Express device A and device B, but we could say that this could be, this could be the CPU talking to our one card connected in one slot. So both of them, as we saw in the previous video, are getting the common the clock signal from the same source, and this signal is transported through the connector to the card. And here we are introduced to the concept of clock data recovery, and that's a key component of any high-speed serial communication, We can find this technology in other protocols. We can find it in Ethernet, in fiber channel. And the concept is simplifying a lot, but basically is that between the data, among the data, encoded into the data, there are bits that are used for clock. And there is a circuit on the receiver end that is going to get a copy of the data, is going to discard, it's going to encode that data, it's going to discard all the data, just looking for the bits that belong to the clock, information. Once this part of the circuit has this clock, it's going to send the clock signal to the logic that is in charge of decoding the data itself. So everything begins with the common clock of 100 megahertz. This could be the main bit that helps to synchronize the system. But the fine clock, the clock that is in charge to go from 100 megahertz to wherever gigahertz required to decode the data, will be extracted from the data itself, shared with the logic that is in charge to decoding the data, and let the magic happen. The magic of increasing over the years, of increasing the speed, keeping the same connector, the same 100 megahertz common signal, because the clock information is inside the data itself. It's not there's not a short explanation. We don't need to go into it, how this is done. There is this video from GoGo Training. This gentleman does a very good job explaining you different ways of encoding data in serial communications. The topic goes into detail in protocols like fiber channel, but the section for 8-bit, 10-bit encoding, decoding is common. It's an IBM standard, and it's a good place to learn about, if you want to go a bit deeper, which I find is interesting, because it's not only the need of mixing the data with clock signals. You need to keep the data changing. You don't want to have, in a serial communication, you don't want to have a lot of zeros or a lot of ones sent at once. You want predictability and variability across the serial interface to keep the signals flowing. And in this video from GoGo Training, there's a nice chunk of information about this topic. This table is from Wikipedia, from the PCI Express page, and here in the section of line code, you have reference to precisely this, of how PCI Express encodes the clock signal into the data, and how and different methods and different standards that they have been using over the years, over the generations of PCI Express. I think starting with 8-bit, 10-bit, it's a good starting point to understand, to learn more about how those techniques works, which I think is part of the clever mechanism of how PCI Express is built, that allows you to keep what's hard to change, those connectors, those common clock signal, helps you to keep those hard to change things in place while doubling data over the years. And I find it very interesting. I hope it was interesting for you as well. So thank you very much.